Okay, welcome you to today's lecture. So, what we were doing last time was we were discussing Bayes and Minimax estimation. So, what a Bayes estimator does is it minimizes the average risk, the average frequentist risk with respect to a given prior distribution. So, heuristically one gets the idea that if your Bayes estimator is minimizing the average risk, it is likely that it minimizes the risk at some points of the parametric space. Now, if it minimizes uniquely the risks at some parametric points, then that means it would be admissible. So, this gives the impression that possibly Bayes rules would be admissible, and that is what we saw, that yes, under certain conditions Bayes rules would be admissible as our heuristic suggested. So, the results which we saw in this direction was, first result was that if you have a unique Bayes rule, then it is always admissible. So, for example, in the case of squared error loss function, you know the Bayes rule which you get, it is through the unique Bayes action. So, it is a unique Bayes estimator. So, under squared error loss function, under non-trivial priors, the Bayes rule would always be Minimax. Sorry, Bayes rule will always be admissible. Then in the case where theta is countable or the parametric space is countable, you realize that if your prior is such that it gives a positive weight to every point in the parametric space, then also Bayes rule is admissible. The third one, which has a lot of applications in the continuous case, this says that if your theta is a subset of Rk, which is open. So, your parametric space is an open subset of k-dimensional equilibrium space, and your risk function is always a continuous function of theta for any decision rule delta with a finite risk. And your prior is such that pi of any open set is greater than 0, and limit infimum of R delta pi naught m. So, if there exists a priors sequence of priors pi m and an estimator delta naught such that limit infimum of R delta naught pi m minus R delta pi m. So, delta pi m is the Bayes rule corresponding to pi m. Pi m by pi m b is 0. This would imply that delta naught is admissible. So, if pi m is a prior on real line, then it said pi m of any open subset of a real line is 0. Now, in real line you know that any open set is a countable union of open intervals. So, it would be sum of those. So, if you can prove that for each of the open intervals pi m a b this quantity is 0, then you are done. So, that means in the case of real line you can replace this b by any open interval. And then as an application of this, we considered the following example. So, x1 x2 xn IID normal theta, let us say sigma naught square. Theta is the unknown parameter, which is whole real line. Sigma naught is known. Now, in this case, we have seen that x bar, so delta naught x, this is x bar, this cannot be Bayes. Any prior. Let me put under squared error loss function. So, my loss function is squared error. So, x bar cannot be Bayes. So, I cannot use that result that if it is a unique Bayes, then it will be admissible. Although under squared error loss function, any Bayes rule is unique. So, it is not even Bayes. So, we cannot use that result. But then this result says even if your estimator is not Bayes, it is a limit of Bayes in this sense. That means its risk with respect to prior pi m minus difference of risk with the risk of the Bayes estimator divided by pi m of AB is 0 for any open set, open interval AB. Then also delta naught would be admissible. So the only thing I have to see is whether I can write down delta naught as limit of Bayes estimators in certain sense or not. So then I realized that I should consider a sequence, a particular prior over here. Now we also realize that in the case of normal distribution, the conjugate prior is again normal. So I considered a prior pi, which was nothing but normal, mu naught and tau naught square. I consider this prior. And then we consider the posterior distribution. The posterior distribution S x given x equal to x turns out to be normal. So in that sense, this normal is a conjugate prior divided by. So it is a convex combination of x bar and this mu naught. So n x bar by sigma naught square plus mu naught by tau naught square n by sigma naught square plus mu naught by tau naught square, and its variance is nothing but n upon sigma naught square plus mu naught upon tau naught square. All right. Now your loss function is squared error. So the Bayes estimator you know is the posterior mean. So delta pi x, the Bayes estimators turns out to be posterior mean. So it is of the type Ax bar plus B. Now A cannot be 0 because A would be 0 only when n by sigma naught square is equal to 0. But what I see is, although I cannot get x bar as a Bayes estimator, but if I take a limit of this, I might get x bar. So limit in what sense I have to get? I should get mu naught to be 0 and tau naught going to infinity. Then n by sigma naught square and you get x bar. So this goes to x bar provided mu is 0 and tau naught square is going to infinity. So this suggests that if I have to use this result, I should choose my priors pi m such that mu naught is 0 and tau naught square is m, and then I take m going to infinity. So I consider pi m, which is normal, 0m. So my Bayes estimator becomes R delta pi m, which is nothing but n by sigma naught square divided by, this is 0, right? So this is not going to contribute, n by sigma naught square x bar upon n by sigma naught square plus, sorry, this is not mu naught upon tau naught square, this is 1 upon tau naught square, right, plus 1 upon m into x bar. So this is the Bayes estimator I get, which is a limit, which in limit gives me the estimator delta naught x bar. So what I need to consider is, to apply this result, I have to consider this difference. So let us consider first R delta naught pi m. Before that, first let us consider the usual risk of R delta naught. So R theta delta naught, which is expected value of x bar minus theta whole square, which is nothing but variance of x bar, which is sigma naught square by n. So it's R theta delta naught does not depend on theta. So when I take its average with respect to theta, I again get sigma naught square by n. So this implies that R delta naught pi m, which is average of this with respect to theta, but theta does not depend on, this does not depend on theta, so this would be sigma naught square upon n naught. Now let us consider what is R theta delta pi m. So let me call this as am times x bar, right? Am is this quantity. Finally, I'll need the order of am. because I have to get this limit. So I need to get the order of AM. So what I get is r theta delta am is expected value of am x bar minus theta whole square. And you know that mean squared error is nothing but variance plus bias square. So variance of am x bar, which is am square times variance of x bar, which is sigma square by n, plus bias square. Bias would be am theta minus theta whole square, because expected value of am x bar is am theta. So that becomes am minus 1 whole square theta square. All right. Now I can get the average risk of this. So r pi m delta pi m. So unlike delta naught, here theta comes. So it would be average of this, so expected value of this. There is no theta, so it would be this as it is, plus expected value of this. This is constant, so expected value of theta square. And the prior for theta square I have taken to be normal 0 m, so expected value of theta square would be m. Sorry, this I have to take 1 by m, right? Normal 0 m, yeah. Sorry, that's okay. So this is same as am square sigma naught square by n plus am minus 1 whole square. Expected value of theta square is nothing but m. So this, yeah, tau naught square goes to infinity. So this is okay. So tau naught goes to infinity. Yeah. So that is what. Yeah. So this is what you get. So now I get the difference of the two. So r delta naught pi m minus r pi m delta pi m would be nothing but the sigma naught square by n minus this. So this is same as sigma naught square upon n minus am square sigma naught square by n plus am minus 1 whole square by m. So this turns out to be 1 minus am square. So I can take 1 minus am common, and then 1 plus am sigma naught by n, 1 minus am square plus 1 minus am times n. All right. So this is the thing. Let us try to see what is my pi m of any open interval. So pi m of AB is nothing but 1 by pi m is normal 0 m. So 1 by root m root 2 pi minus infinity to infinity e to power minus 1 by 2 m theta square d theta. Sorry, this would be a to b. All right. Note that if there was no root m over here, I take limit m going to infinity, bounded convergence theorem would hold because of exponential over here. You can take the limit inside, m going to infinity, it becomes e to power minus 0, which is 1, it becomes b minus a. So that means root m times limit m going to infinity of root m times pi m a b is nothing but b minus a by root 2 pi. So if I have to get this limit, I multiply numerator and denominator both by root m. So let us consider, let me call this as star. So star is same as limit m going to infinity of root m into r delta naught pi m minus r delta pi m upon root m pi m ab. Now, I know that this goes to some constant. So, if I can show that numerator goes to 0, I am done. So, that means I have to find root m r delta naught pi m minus r delta pi m pi m. Now, this difference is over here. So, what I need to do is I need to just find out the orders of am. Am is this quantity. So, let me write it down. So, this is am, right? This whole is am. Am is this quantity because nowhere else am is coming in this. Only am is coming over here. So, this is sigma naught square by n. Now, n by sigma naught square I can take outside. Then this becomes 1 plus, sigma naught square by n m to power minus 1. Is it okay? This I take outside, sigma naught square. Now, m large, this is going to be a small quantity. So, this is n by sigma naught square. And then 1, I expand it, 1 plus x to power minus 1, x is mod of x is less than 1 for logs m. So, 1 minus sigma naught square by 1 by m plus higher orders of 1 by m square. So, it is 1 plus capital O 1 by m. Capital O m means the order of 1 by m plus higher orders. Okay. So, what do you get? Let us see over here. R delta naught pi n is sigma naught square by a n minus am x bar m sigma naught square by m plus am square. This is this quantity. Okay. If you want 1 minus am into 1 plus, each time I mess up something over here, but let us just check that once again. 1 minus am goes outside, am goes to n by sigma naught square, so it goes to, so that will not be an issue because am is finally going to 0 as, sorry, n by sigma naught square. So, this would be 1 minus n by sigma naught square, so that is not an issue. 1 plus am is n by sigma naught square and n by sigma naught square, so that would also go to some quantity, and 1 minus am into am. I have to multiply this by root m also. So, root m, let us write down. So, root m r delta naught pi m minus r delta pi m pi m. This becomes root m one minus am 1 plus am sigma naught square by an. Yeah. So, how much do you get? So, root m into all that. So, 1 minus am. 1 minus am is nothing but 1 minus n by sigma naught square plus little o 1 by m, right, divided by 1 plus am. 1 plus am is nothing but 1 plus n by sigma naught square plus little o 1 by m into sigma naught square by n plus 1 minus am into m. So, just try to check that this should go to 0. The only trouble is when you do it in the board, there is possibility that you might have missed few terms over here and there. But the idea is simple. So, root m r delta naught pi m minus r delta pi m you have to go to 0. R delta naught pi m we have already seen is sigma naught square by n. R pi m delta pi m is nothing but am x bar. Am x bar we have seen is nothing but n by, yeah, that is where the problem is. So am is n upon sigma naught square upon n by sigma naught square plus 1 by m. So you have to be just a little bit careful. I have taken n by sigma naught square everything outside. So there is no n by sigma naught square over here. So it is am is only 1 plus little om. Right. Now then things become simpler. Yeah, that's what happens when you are struggling with expressions on a board. One small term you miss and then there is a problem. So I made a problem that n by sigma naught square I took outside, but n by sigma naught square will be taken outside from numerator, denominator both. So that would be gone. So only you will be left with 1 plus sigma naught square by nm to power minus m, which is nothing but 1 plus capital O 1 by m. All right. So this is nothing but root m. Now r delta naught pi m minus r delta pi m is this quantity. So which is to begin with 1 minus am. 1 minus am is same as little o 1 by m. Then 1 plus am. 1 plus am is nothing but 2 plus little o 1 by m into sigma naught square by n plus 1 minus am into m. 1 minus am into m would be m times. Good. Now this would go to 0 because root m and order of 1 by m. So root m 1 by root m, this would be order of 1 by root m. So that would always go to 0. 2 goes to 2, this goes to 0, so this goes to 2 sigma naught square by n, and m little o 1 by m would go to some constant. So this goes to 0. And this anyway you have shown that is some goes to constant. So this is going to 0. So this implies that delta pi x is equal to x bar is admissible. So in certain situations you might have a limit of a Bayes estimators which turns out to be admissible. So this was about, so now let us come to the minimexity. So it looks like minimexity is also deals with an estimator which minimizes the maximum risk. Now if it minimizes the maximum risk and your risk function is a continuous kind of a thing, then it looks like it will maximize the risk function at some theta. If that is the case, then minimax estimators would also be admissible under certain conditions, especially if your risk function is very nice and so on.